The workshop smelled of oil and burning metal. 600 miles from the nearest combat zone, in a converted airplane hangar outside Albuquerque, New Mexico, a team of American engineers was about to change the course of the air war. It was March 1944, and scattered across their work tables lay the remnants of a dying B-17 bomber. Twisted aluminum skin, hydraulic pistons, and shattered instrumentation panels. Within 90 days, these fragments would become the guidance system for a weapon that could hunt its target through smoke and darkness, following heat signatures invisible to the human eye. The Germans called their factories untouchable. The Japanese believed their industrial centers were beyond the reach of precision bombing. Both were wrong. This is the story of Operation Ferris Eye, the classified program that turned America's scrap metal into the first thermal tracking bombs, and how a handful of civilian engineers, armed with slide rules and salvaged parts, gave the Allies a weapon that could see in the dark. Before we continue the story of how American ingenuity transformed junkyard scrap into precision-guided fury, make sure to hit that subscribe button and tell me where you're listening from, which city, which state. I'm curious to know who's brave enough to discover what happened when engineers decided that bombs should think for themselves. The concept began with failure. In February 1944, the 8th Air Force flew 317 bombers over Schweinfurt, Germany, targeting the ball bearing plants that kept the Wehrmacht's tanks rolling. 260 aircraft returned. Of those, 43 were so badly damaged they never flew again. The bombs, conventional Mark 82 500-pounders, fell within an average of 400 yards of their aim points. Only 11% struck within the factory complex. The rest cratered farmland, destroyed civilian housing, or disappeared into the Bavarian forests. In the briefing rooms of Wright Field, Ohio, the arithmetic was brutal. At this rate, the Allied strategic bombing campaign would run out of bombers before Germany ran out of factories. Something had to change, and it couldn't wait for the war to end. Major Daniel Kessler had been a mechanical engineer at General Electric before Pearl Harbor. Now he wore the uniform of the Army Air Forces and carried the weight of 60,000 aircrew lives on his conscience. He stood in the converted hangar that served as the Applied Munitions Laboratory, watching 36 engineers, most of them civilians pulled from Detroit's automotive plants, Pittsburgh's steel mills, and New York's electrical manufacturers, attempt to solve a problem that had defeated every weapons designer since the Wright brothers first imagined dropping explosives from aircraft. The challenge was simple to state and seemingly impossible to achieve. Make a bomb that could adjust its trajectory after release, tracking a target by its heat signature, rather than relying on the bombardier's aim and luck. The obstacle wasn't imagination, it was resources. Copper was reserved for shell casings. High-grade steel went to armor plate. Advanced electronics were allocated to radar sets and radio navigation systems. If Kessler's team was going to build a guided bomb, they would have to build it from whatever the scrap drives could provide. Sarah Chen had emigrated from Shanghai in 1937, fleeing the Japanese invasion with her family's engineering texts and her father's pocket watch. By 1944, she was one of 43 women working in the Applied Munitions Laboratory, her degree from MIT making her one of the most qualified thermodynamics specialists in the American Southwest. She stood at a workbench littered with salvaged thermocouples, temperature sensors pulled from damaged aircraft, and sketched calculations on a chalkboard that had once taught geometry to high school students in Amarillo. The principle was sound. When metal heated, it generated a weak electrical current. A sensitive enough instrument could detect the temperature differential between a factory smokestack and the surrounding air. If they could build a device that translated that heat signature into mechanical motion, they could steer a bomb toward the hottest point in its field of view. The difficulty was sensitivity. The thermocouple junctions needed to detect temperature differences of less than 10 degrees Fahrenheit at distances exceeding 1,000 feet, all while tumbling through the air at 300 miles per hour, subjected to wind shear, vibration, and the concussive shock of their own release from the bomb bay. And they had to build it from scrap. Across the hangar, Technical Sergeant Frank Kozlowski was constructing what would become the bomb's control surface assembly. Before the war, he had welded frames for Studebaker sedans in South Bend, Indiana. Now he was adapting the aileron mechanisms from a salvaged P-38 Lightning, modifying the control linkages to respond to electrical impulses rather than pilot input. The aluminum came from a bomber that had crash-landed in Nevada 3 months earlier, its crew walking away, but the airframe too damaged for reconstruction. The hydraulic cylinders came from a bulldozer that had pushed its last load of dirt at a training base in Arizona. The electrical wiring, copper filament wrapped in fabric insulation, had been stripped from the walls of a barracks scheduled for demolition. Kozlowski worked with the methodical precision of a man who understood that sloppy welds killed people. Each joint was measured, tested, retested, and documented in notebooks that would eventually fill 3 filing cabinets in the National Archives. This wasn't innovation for innovation's sake. This was desperation engineering, the kind that happens when brilliant people have insufficient resources and unlimited motivation. The theoretical framework came from a Cornell University physicist named Dr. Raymond Atwater, who had published a paper on infrared detection in 1938 that approximately 7 people had read before the war began. Now that paper was classified secret and formed the foundation of 3 separate weapons development programs. Atwater had joined the Manhattan Project initially, working on isotope separation. But the Applied Munitions Laboratory had borrowed him for 6 weeks to solve their guidance problem. He worked 18-hour days, sustained by coffee that tasted like transmission fluid, and the knowledge that every day the bombs remained unguided, more crews failed to return from Europe. His breakthrough came not from advanced theory, but from backwards thinking. Instead of trying to detect faint heat signatures at long range, he proposed getting the bombs closer first. The weapon would fall ballistically for the first 15 seconds after release, giving it time to stabilize and acquire speed. Then, at an altitude of 3,000 feet, low enough for thermal contrast to be pronounced, but high enough to allow steering corrections, the guidance system would activate. A spinning mirror assembly, salvaged from a damaged search radar unit, would scan the ground below in a circular pattern. When the thermocouples detected heat exceeding ambient temperature by a threshold margin, the control surfaces would adjust, angling the bomb toward the source. It wouldn't be perfect, but it would be better than dumb iron falling through hope and prayer. The first prototype weighed 643 pounds, including the Mark 82 bomb casing and 200 pounds of Composition B explosive. The guidance package added another 97 pounds, far heavier than Kessler had wanted, but unavoidable given the materials available. They painted it dull gray and stenciled TC-1 on the tail fin. Thermal guided, Prototype 1. The test range was 60 miles south of Albuquerque, in terrain so desolate that locals joked the scorpions had left for better opportunities. The target was a steel drum filled with burning diesel fuel, producing a heat signature approximating a locomotive or small factory boiler. The bomber was a war-weary B-24 Liberator, flown by a test pilot named Captain James Halloran, who had survived 31 combat missions over Germany and considered experimental weapons testing a comparative vacation. At 10,000 feet, with the New Mexico sun turning the cockpit into an oven, Halloran lined up on the smoke column rising from the target drum. The bombardier, a lieutenant from Minnesota who normally taught navigation, called out the countdown. At release, the TC-1 fell away, tumbling slightly before the tail fins stabilized its descent. For 15 seconds, nothing happened except gravity and momentum. Then, at 3,000 feet, the guidance package activated with a faint electrical hum that nobody on the ground could hear over the wind. The bomb missed by 78 feet, cratering the desert 200 yards past the target drum. Atwater called it a disaster. Kessler called it a beginning. The guidance system had activated. The control surfaces had moved. The bomb had attempted to steer. It had simply steered too late and overcorrected, the crude mechanics unable to compensate for the weapon's terminal velocity. But the principle was proven. Heat could guide a falling bomb. They just needed to make it work faster, smoother, and with less mass. They had 12 weeks before the program review that would determine whether Operation Ferris Eye received continued funding or joined the dozens of other promising ideas that died in the limbo of wartime prioritization. Kessler called a meeting for 200 hours. Nobody complained. They all knew what failure meant. It meant more bombers lost, more crews that didn't come home, more cities that remained intact to produce the guns and tanks that killed Allied soldiers. Failure was unacceptable. The solution came from an unexpected source. Private First Class Theodore Washington had been assigned to the Applied Munitions Laboratory as a mechanic, maintaining the vehicles and equipment that kept the facility running. Before the draft, he had worked for the Pennsylvania Railroad, repairing locomotive governors, the mechanical speed regulators that prevented trains from running away on downhill grades. Governors used centrifugal force and spring tension to modulate power without human intervention. They were simple, reliable, and required no electrical power. Washington approached Sergeant Kozlowski during a cigarette break and asked whether anyone had considered using a mechanical governor to prevent the guidance system from overcorrecting. Kozlowski had not. Neither had Atwater. Within 48 hours, Washington was promoted to corporal and assigned to the design team. His governor mechanism used a flyweight assembly salvaged from a destroyed truck engine, calibrated to limit how quickly the control surfaces could move. The system added only 4 pounds to the overall package and required no additional power supply. It was elegant, simple, and entirely constructed from parts that had been destined for the salvage yard. TC-2 was assembled in 16 days, incorporating Washington's governor and a refined thermocouple array that Chen had optimized by testing dozens of junction configurations. The new sensor array used wire salvaged from damaged radio sets, soldered together in a pattern that increased sensitivity by 30%, while reducing weight by 11 pounds. The test was scheduled for April 12, 1944 at dawn, when the temperature differential between the desert floor and a burning target would be most pronounced. Captain Halloran flew the same B-24, now christened Hopeful Monster by the ground crew. The target was a pair of oil drums, burning diesel and producing a heat signature visible to the naked eye as a shimmer in the morning air. At release, TC-2 fell clean. The telemetry package strapped to its tail, broadcasting altitude, velocity, and control surface positions to the receivers on the ground. 15 seconds of ballistic fall. Then activation. The control surfaces twitched, making microscopic adjustments. The bomb's trajectory curved, subtle but definite, angling toward the heat source. Washington's governor kept the movements smooth, preventing the wild overcorrection that had doomed TC-1. At 200 feet, the bomb was tracking perfectly, aimed directly at the burning drums. It struck 12 feet from center, well within the lethal radius for any industrial target. The explosion sent a mushroom of dust and smoke into the dawn sky. On the ground, the engineering team stood in silence for 3 seconds before someone started clapping. Then they were all clapping, cheering, shaking hands, and calculating how quickly they could build 50 operational units. But proving the concept was only the beginning. The path from a single successful test to combat deployment involved solving 1,000 smaller problems, each potentially catastrophic. The guidance system needed to function in rain, through clouds, in turbulence that could rip the wings off an aircraft. It needed to distinguish between the heat signature of a factory and the heat signature of a burning field. It needed to survive the shock of release, the cold of high altitude, and the vibration of a bomber at full power. Most critically, it needed to be manufactured at scale, using materials that wouldn't divert resources from other critical weapons programs. Kessler presented the results to a review board at Wright Field in late April. The board included 2 generals, a Navy captain, and 3 civilian scientists from the National Defense Research Committee. They watched the test footage twice, reviewed the telemetry data, and asked pointed questions about reliability, cost, and production timelines. Could the guidance package survive shipboard transport to England? Could it be attached to existing bomb stocks without modification? Could bombardiers be trained to use it without extensive requalification? Kessler answered each question with data, specification sheets, and the quiet confidence of a man who had seen his weapon work. The board approved expanded testing and authorized funding for 20 pre-production units. Operation Ferris Eye was officially a program of record. Production began in May 1944, using a commandeered warehouse in Pueblo, Colorado, that had previously manufactured agricultural equipment. The workforce was a mixture of defense plant workers, Army Air Forces mechanics, and civilian volunteers recruited from local high schools and universities. The assembly line was organized by Chen, who applied principles she had learned studying industrial engineering at MIT, modified for the reality of building precision weapons with non-precision tools. Each guidance package required 147 individual components, sourced from scrapyards, salvage depots, and damaged equipment from 37 different military installations. Thermocouples came from aircraft instruments. Control surface actuators came from bomber trim tab assemblies. Electrical relays came from field telephones. The spinning mirror mechanism came from damaged radar sets. Every component was tested individually, then tested again after installation. The reject rate was 43% in the first week, falling to 18% by the end of the month, as workers developed expertise and processes improved. Each completed guidance package was logged, numbered, and matched with a specific bomb casing. By late June, the warehouse was producing 6 units per day. By August, 12. The weapons were designated Bomb-Guided Thermal M44 in official documentation. But everyone involved called them Ferris Eyes, or simply Eyes. The first combat unit was shipped to England in September 1944, packed in wooden crates marked Fragile Instruments, and accompanied by a 12-man technical team led by Sergeant Kozlowski. Their destination was RAF Bassingbourn, home to the 91st Bombardment Group, which had been flying B-17 missions over German industrial targets since 1942. The group commander, Colonel Eugene Morrison, was skeptical. He had seen promising weapons fail in combat, had watched crews die because some engineer's brilliant idea didn't work when German flak was exploding around the aircraft. But he was also pragmatic. If these bombs worked as advertised, they could reduce losses and increase effectiveness. He authorized 10 aircraft to be equipped with modified bomb racks capable of carrying the M44s. The crews were briefed on the new weapons in a Quonset hut that smelled of cigarette smoke and damp wool. The bombardiers listened with the focused attention of men whose survival depended on their equipment functioning perfectly. The Ferris eyes would only work against certain targets: factories with active blast furnaces, power plants with coal-fired boilers, oil refineries with burning waste gas. But for those targets, the accuracy would be unprecedented. Instead of dropping dozens of bombs and hoping for hits, they could drop 12 and expect results. The first combat mission was flown on September 23, 1944, targeting the Krupp Steelworks in Essen, Germany. 8 B-17s, each carrying 2 M44 bombs, crossed the English Channel in formation with a larger strike package of conventional bombers. The weather was scattered clouds at 8,000 feet, with moderate flak expected over the target. Major Robert Sinclair, leading the Ferris Eye element, checked his bombardier's intercom at intervals, confirming the guidance systems were armed and ready. The target came into view at 10:15 in the morning, a sprawling complex of blast furnaces, rolling mills, and fabrication shops, smoke and steam rising from dozens of stacks. The bombardiers synchronized their Norden bomb sights, made wind calculations, and prepared for release. At 10,000 feet, Sinclair gave the order. 16 M44 bombs fell from the formation, tumbling clear of the aircraft before their guidance systems activated. From the ground, German observers saw something they had never witnessed before: bombs that curved in flight, arcing toward the hottest points in the complex as if drawn by invisible wires. 8 of the 16 bombs struck within the factory complex. 5 hit active blast furnaces, destroying critical equipment and killing the production of armor plate for 3 weeks. The remaining 8 bombs fell outside the target area, victims of guidance failures or insufficient heat signatures. But 8 hits from 16 bombs represented a strike percentage 4 times better than conventional weapons. The crews returned to England with minimal damage, having spent less time over the target and faced less concentrated fire. Mission success. By November 1944, the 91st Bombardment Group was flying weekly missions with Ferris eyes, targeting German industrial centers that Allied intelligence identified as critical to the Wehrmacht's ability to resist. The bombs weren't perfect. Guidance failures occurred in approximately 20% of drops, usually from mechanical damage during transport or electrical failures at altitude. But even with the failures, the M44s were achieving hit rates that conventional bombing could never match. The Germans noticed. Intelligence reports intercepted by ultra codebreakers showed increasing concern about American heat-seeking bombs and orders to reduce visible emissions from factories during daylight hours. Some facilities installed smoke generators to obscure heat signatures. Others built dummy furnaces that produced heat but no useful production, hoping to draw bombs away from critical equipment. It was a tactical adaptation to an unexpected threat, proof that the Ferris were having an effect beyond their immediate damage. The 8th Air Force requested 300 additional units. The Applied Munitions Laboratory, now expanded to a staff of 217, began working in shifts to meet the demand. The scrap drives that had collected old pots, pans, and bicycle frames from American homes were now feeding a production line that turned civilian donations into precision-guided weapons. It was the ultimate expression of the home front contributing to victory. Grandma's broken radio becoming the guidance system that knocked out a German oil refinery. The program remained classified throughout the war. Crews were briefed under secrecy orders. After-action reports used code words. Even the bombs themselves bore no external markings that would identify them as anything other than standard munitions. The secrecy served multiple purposes. Operational security, obviously, but also strategic misdirection. As long as the Germans believed the improved accuracy was due to better training or luck rather than technology, they wouldn't know to prioritize countermeasures. The deception worked. Post-war interrogations of German industrial managers revealed that many never realized they were being hit by guided weapons. They attributed the increased accuracy to improved Allied training or better weather conditions. Some suspected radar guidance, but none correctly identified the thermal tracking mechanism. The secrecy also protected the engineers. If the Germans had understood how simple the Ferris-I design was, how it relied on salvaged parts and basic thermodynamics, they might have developed their own version. As it was, German guided weapon programs focused on complex radio guidance systems that required extensive infrastructure and were vulnerable to jamming. The Americans had succeeded by thinking smaller and building simpler. By the time of Germany's surrender in May 1945, the Applied Munitions Laboratory had produced 847 M44 guidance packages. 512 had been delivered to England. 391 had been dropped in combat. 276 had achieved direct hits on their intended targets, a success rate of 70% compared to 11% for conventional bombs against similar targets. The confirmed destruction included 17 blast furnaces, 12 synthetic oil plants, 23 railroad marshalling yards, and 8 Luftwaffe airfields where burning fuel tanks provided perfect heat signatures. The cost was negligible compared to the alternative. Each M44 cost approximately $240 in parts and labor, using materials that would otherwise have been scrapped. A conventional bombing raid achieving equivalent destruction would have required 10 times as many aircraft, with corresponding losses to flak and fighters. The Air Force calculated that Ferris-I's had saved at least 63 bombers and 630 crew lives by reducing required exposure time over targets. That calculation didn't include the German workers who didn't die because fewer bombs fell on civilian areas, or the Allied soldiers who didn't die because German factories produced less ammunition. The indirect effects were impossible to quantify, but undeniably real. The program was declassified in 1963, when the technical details were no longer militarily sensitive and guided missiles had advanced far beyond the crude thermal tracking of the M44. The surviving engineers were finally able to talk about their work. Major Kessler, retired and teaching mechanical engineering at Purdue University, gave interviews describing the desperate scramble to build weapons from salvage. Sarah Chen, working for Boeing's missile division, explained the thermodynamic principles in technical papers that became standard references for guidance system designers. Corporal Washington, back working for the Pennsylvania Railroad, was featured in a magazine article about unsung heroes of the home front. Sergeant Kozlowski opened a machine shop in Indiana, occasionally building custom parts for aerospace companies and refusing to discuss his war work beyond acknowledging he worked on bombs.
The Applied Munitions Laboratory was dismantled in 1946, its warehouse in Pueblo returning to agricultural equipment production. The hangar in Albuquerque became a storage facility for surplus aircraft parts, then a community college technical training center. No markers indicated what had happened there. The only memorial was in the memories of the men and women who had turned scrap metal into precision weapons, and in doing so, shortened the war. The M44 Ferris Eye was never used in combat again after Germany's surrender. The planned deployment against Japanese targets was overtaken by events. The atomic bombs dropped on Hiroshima and Nagasaki ended the war before conventional bombing campaigns could be expanded. The remaining inventory of guidance packages was placed in storage at Anniston Army Depot in Alabama, where they remained until 1957, when they were finally scrapped and recycled. By then, the technology was obsolete. Modern guided bombs used radar, television guidance, and increasingly sophisticated infrared sensors that made the crude thermocouple arrays of the Ferris Eye look like ancient history. But the principle remained valid. Heat signatures could guide weapons. Simple mechanisms could achieve precision. Salvaged materials could win wars. The engineers who had worked on Operation Ferris Eye went on to design the Sidewinder heat-seeking missile, the Maverick television-guided bomb, and the Paveway laser-guided munitions that dominated later conflicts. They brought with them the lessons learned in that converted hangar in New Mexico, that innovation doesn't require unlimited resources, that desperate times produce creative solutions, and that ordinary people, mechanics, welders, refugees, and mathematicians can accomplish extraordinary things when the stakes are high enough and the goal is clear. In 1994, the Air Force Historical Research Agency declassified the full operational records of Operation Ferris Eye, making available to researchers the technical specifications, test results, and combat reports that had been sealed for 50 years. The documents revealed details that had been forgotten or misremembered. The program had employed 473 people at peak production. It had consumed approximately 18,000 pounds of salvaged material, including aluminum from 47 damaged aircraft, copper from 320 miles of stripped wiring, and steel from 19 destroyed vehicles. The total program cost was $187,000, less than the price of a single B-17 bomber. The efficiency was staggering. For less than 0.2% of the 8th Air Force's budget, Operation Ferris Eye had increased bombing effectiveness by 300% against specific target categories. It was arguably the highest return on investment weapons program of the entire war, achievable only because the engineers had been forced to work with scrap rather than pristine materials. Limitation had driven innovation. Scarcity had produced genius. The very constraints that seemed insurmountable had become the foundation of success. Today, the thermal guidance principle, pioneered by the Ferris Eye, is standard technology. Every heat-seeking missile, every infrared targeting pod, every thermal imaging system traces its lineage back to that converted hangar in New Mexico, where civilian engineers
tried to make bombs think. The technology has advanced beyond recognition. Modern sensors can detect temperature differences measured in thousandths of a degree, can track targets from dozens of miles away, can distinguish between real heat sources and decoys. But the fundamental concept remains unchanged. Heat can betray a target, and properly designed weapons can follow that heat to impact. The innovation of 1944 was proving the concept was possible. The innovation of the decades since has been refining the execution.
But none of it would exist without those first crude prototypes, built from salvaged thermocouples and bomber parts, falling through the New Mexico sky toward burning oil drums, proving that American ingenuity could turn junk into precision and scrap metal into victory. The men and women of Operation WWII never received medals. Their work was too classified for public recognition, and by the time the secrecy was lifted, most had moved on to other projects and other lives. But they changed warfare permanently. They proved that precision didn't require complexity, that effectiveness didn't require expense, and that innovation was possible even under the most restrictive conditions. They took the scrap metal that American families donated to the war effort, the old pots, the broken appliances, the worn-out cars, and turned it into weapons that could see in the dark and strike with unprecedented accuracy. They gave bomber crews a better chance of survival. They shortened the war, saved lives on both sides, and demonstrated that sometimes the best solutions come not from unlimited budgets and perfect materials, but from brilliant people working with whatever they have, driven by necessity and guided by determination. That is the true legacy of Operation WWII, not the bombs themselves, which became obsolete within years, but the proof that limits are often just challenges waiting to be solved, and that the greatest innovations sometimes come from turning constraints into opportunities. The workshop in Albuquerque is gone. The warehouse in Pueblo manufactures tractors again. The bombs themselves are dust. But the principle endures. Heat seeks, metal guides, and American engineers find a way.